Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Delhi University. Today we are going to discuss about the module Other Device Structures and Solar Concentrators from the paper Energy Related Materials. The main points which will be covered in this module are: first, the differences between the homojunction and the heterojunction. Secondly, we will discuss the metal semiconductor junction cell. Thirdly, what are photovoltaic concentration and their application in solar cell technology. Let us start with a brief introduction about the module. The photons of energy more than the energy gap incident on the semiconductor will produce electron-hole pairs. If they are not stimulated to move apart, they will eventually recombine in a time dictated by the lifetime of the material. The electron-hole pairs, they are separated by the application of electric field, which produces space charge resulting in the voltage across the junction called as the photovoltage. The photocurrent will follow when these charge carriers are allowed to flow in an external circuit. So the three methods for generating the internal electric field to separate the electron-hole pairs are: first, the homojunction or PN junction; second, heterojunction; third, metal semiconductor heterojunction. There are other techniques also for generating the internal electric fields, such as: first, introducing strains or any other local impurity variations; second, the photomagnetoelectric effect, the so-called Hall effect; third, anomalous photovoltaic effect; and fourth is Denver effect, which is due to the differential diffusivities of the charge carriers. We shall here discuss the electrical characteristics only of the PN junction, the heterojunction, and the Schottky junction. These are commonly used. The PN or NP junction cell. The PN junction solar cell structures are formed by joining the same type of materials doped with different dopants on either side of the junction. The characteristic and the energy band diagram of a PN junction is shown in the figure. The conventional solar cells are homojunction solar cells. As discussed earlier, the PN junction cell is created by the diffusion of the N-type material into a base of P-type. A junction is formed at the interface where the dominant dopant changes to the opposite type by transferring, and in this region a space charge is created that maintains the net electron and the hole currents at zero. So this region is called as the depletion region. The heterojunction cell. The heterojunction cells are made by joining the two materials of different energy band gap. Now a simple energy band diagram of a heterojunction is shown in the figure, where the two materials are joined together to give the final energy band diagram, which is shown below. In this material, a technique of gaseous or liquid epitaxy is employed, where the materials of desired dopants are grown into a base crystal by deposition from a gas or a liquid. The heterojunction cell, it can be seen that there are two notches, one in the conduction band and one in the valence band, as shown in the previous figure, and their heights are given by delta EC is equal to chi2 minus chi1 and delta EV is equal to Eg1 minus Eg2 minus delta EC, where chi2 and chi1 are the electron affinities of the two heterojunction cell. This cell structure has three main current mechanisms. First is the diffusion current due to the injection of minority carriers from each side of the junction, similar to PN junction cell. Second, current within the space charge region due to generation recombination. And third is the current due to tunneling. So the expression for the diffusion current for NP heterojunction is given by ID is equal to IOH multiplied by exponential of QVD by KT minus 1, where VD is the voltage across the junction and IOH is the saturation current, and they are given by VD is equal to V minus IRD and IOH is equal to Q DENI square by LENA multiplied by XT. Here V is the voltage as in a PN junction. RD is the sum of the lead and the internal diode series resistances. XT represents the carrier transmission from one material to another, and I is the current. Generally, during device operation, the generation recombination current is small as compared to the diffusion current, and it is given by Ig is equal to Ig prime sine hyperbolic QV by 2 KT, where Ig prime depends on the doping level, the temperatures, and the impurities in the semiconductor. For a single deep level recombination center, Ig prime can be written as Ig prime is equal to Qni by tau kT by Q Emax. It is equal to Qni kT xc divided by tau Q Vb, where tau is the lifetime of minority carriers, Emax is the maximum depletion layer field strength, and Vb is the built-in potential, which can be written as Vb is equal to kT by Q ln of any nh by ni square. So the expression for the tunneling generally during device operation, the generation recombination current is small as compared to the diffusion current,
by 3 pi
and it is given by
multiplied by
Ig
square
is
root
equal to
of m
Ig
star
prime
e by
sine
Vd,
hyperbolic Qv
where
by
nt
2 kT,
is a constant
where Ig
depending
prime
upon
depends on the doping
density
level,
of
the
allowed
temperatures, and the
N is the
impurities in the
impurity density,
semiconductor.
m star is the
For a
effective
single
mass,
deep level
Ki is the
recombination
constant
center,
depending on the
Ig
dielectric
prime can be
constant,
written as
effective mass
Ig
and
prime is equal
built-in
to
potential.
Qni by tau kT by Q Emax. It is equal to Qni kT xc divided by tau Q Vb, where tau is the lifetime of minority carriers, Emax is the maximum depletion layer field strength, and Vb is the built-in potential, which can be written as Vb is equal to kT by Q ln of any nh by ni square. So the expression for the tunneling current can be written as It is equal to Ki nt multiplied by exponential of 2 pi by 3 pi multiplied by square root of m star e by Vd, where Nt is a constant depending upon the density of allowed states, N is the impurity density, m star is the effective mass, Ki is the constant depending on the dielectric constant, effective mass, and built-in potential. Metal semiconductor junctions or Schottky junction. So students, as you can see, this figure shows the sequential representation of the different stages of the formation of metal semiconductor junction, basically a Schottky junction. So all these figures represents the energy band diagram of a metal semiconductor heterojunction. Metal semiconductor junctions or Schottky junction. Metal semiconductor junctions, so called the Schottky junctions, are formed when a metal is brought in contact to a semiconductor. So after making the contact, a potential drop takes place due to the charge carrier transformation in the contact region to account for the work function differences. As there is a huge difference in charge carriers in the metal and the semiconductor, hence a potential drop on the semiconductor side of the junction is produced, giving rise to a depletion region at the interface similar to that in a PN junction. Such junctions in a metal and semiconductor are called as the Schottky junctions. So in the previous figure, there was a phi b which is nothing but the barrier voltage, which depends on the surface states at the interface. Due to the huge difference in the vacuum work functions in a metal, that is Φm, and a semiconductor Φsc, the energy band in the semiconductor bends accordingly. The position of the minority charge carriers in the semiconductor is the same as that of the p-n junction. So for n-type semiconductor, the current due to the minority carriers can be written as IOH is equal to QDH Ni square by LH Nd multiplied by exponential of QV by KT minus 1. The only obstacle for the flow of majority carriers between the metal and the semiconductor is the depletion region potential barrier at the interface. The height of the depletion region at the interface varies with the applied voltage. The emission of electrons from the semiconductor in the case of metal on n-type barrier, or the emission of holes from the semiconductor in case of metal on p-type barrier, is a function of thermionic emission and diffusion. The expression for thermionic emission for the metal on n-type semiconductor can be written as IOE is equal to A star T square exponential of minus Q phi b by KT multiplied by exponential of QV by KT minus 1, where A star is the effective Rickardson coefficient. So from the above, it is confirmed that the magnitude of majority carrier current depends on the height of the barrier voltage phi b at the interface. This majority carrier component is generally much larger than the minority carrier component. Hence, larger the barrier phi b will result in a better performance of a cell. Hence, the metal work function is selected in such a way that can provide a large barrier height at the metal semiconductor interface. However, it is found experimentally that for several semiconductors, the size of the barrier induced is independent of the work function of metal. This can happen due to the variety of reasons such as lattice mismatch or contaminants on the semiconductor surface. The Schottky junction can be made very easily as there is no p-n junction formation involved over here. Photovoltaic concentrating system. The possible approaches of reducing the cost of photovoltaic power, which is produced from the solar cell, is either by using a high efficiency solar cell or by reducing the size of the cell using concentrated sunlight. So the electrical power obtained from the solar cell module can be increased several times as by using suitable type of solar energy concentrator. This will enhance the radiation intensity by about 100-fold. Hence, the cost of the electrical power can be decreased many folds by using solar concentrators. So one need to be very careful while deciding the type and the size of the concentrator due to various reasons such as: first, the operating current increase with the light intensity, and therefore if the series resistance is of the order of 0.01 ohm, the electrical power generated would be dissolute within the cell without much gain. Hence, the series resistance losses must be reduced to get the higher electrical current. Second reason is that concentrating the sunlight on a solar cell will also tend to increase its operating temperature, resulting in lowering in the cell efficiency. Hence, some kind of passive or active cooling device is adequate for the concentration ratio of about 50 to remove the thermal heat from the solar cell. So the active cooling is required for higher concentration ratio. Third reason is that the solar cell with smaller band gap like silicon is not suitable for concentrated solar radiation, since the operating temperature of the cell depends on the band gap of the material. However, solar cell with higher gallium arsenide faces a smaller drop in efficiency with the increase in temperature. So the efficiency of gallium arsenide remains at 10% even at a temperature of 250 degrees Celsius. Photovoltaic concentrating system. The efficiency of gallium arsenide remains at 10% even at a temperature of 250 degrees Celsius. Solar cell based on gallium arsenide material was studied under various situations, such as under concentrated solar radiations, under photovoltaic concentrators, under the effect of light intensity, and under the effect of temperature. As discussed earlier, at a fixed cell temperature, the short circuit current and the open circuit voltage increases with increasing solar intensity on the cell, and hence the fill factor also increases. The high efficiency in solar cell, it can be observed only at a low value of series resistance of the cell. Otherwise, there will be a large loss in the efficiency. The cost of the cell and concentration ratio decides which kind of solar cell will be used under concentrated solar radiation. For example, if the concentration ratio is less than 100, then their meaning of using the gallium arsenide solar cell as the performance of silicon solar cell is also satisfactory in that case. However, if the concentration ratio is more than 100, then silicon solar cell should not be used and the only choice is of gallium arsenide solar cell. The most recommended solar energy concentrators for solar cells are linear concentrators, point focus concentrators, compound parabolic concentrators, and plane mirror boosters. All linear, point, and stationary concentrators, they have advantages and disadvantages. The manufacturing of stationary concentrators with concentration ratio below 3 is easy and simple. The concentrators for seasonal use, simplest one, and can give a concentration ratio up to 12. Both the stationary and periodically adjusted concentrators are used. Linear parabolic troughs with single axis tracking can be employed when high concentration ratio is not required. There are various firms which are manufacturing point focus Fresnel lenses pre-prepared out of acrylic sheet to use as the concentrator. Heat generated during the device operation, it can be removed either by the active or the passive means. In the active cooling, generally it is done by water or air which is circulated behind the solar cells, and it is used where the concentration ratio is quite high, resulting in the cell temperatures more than 100 degrees Celsius. Passive cooling, which is quite effective, is employed when the concentration ratios are low and cell temperature is less than 100 degrees Celsius. Here some kind of the films is attached to the cell base to accomplish the cell cooling by dissipating the heat to the surroundings. Recently, new concept has been adopted to combine the photovoltaic and the thermal, that is PVT, where the photovoltaic module is attached on a flat base through which air to water is circulated, and the heated water can be used for other different applications. Hence, these PVT units appear to be more promising since Both the electric power and thermal energy are produced simultaneously. Several research grants funded and projects have been distributed by this Department of Energy for the development of solar photovoltaic concentrator system. In these systems, solar cell efficiency is the more critical parameter than the cell fabrication cost. Concepts based on using the materials with different band gap to convert different part of solar spectrum are likely to result in enhanced efficiency. So students, let us summarize what we have learned in this module. There is a wide range of photovoltaic device structural possibilities apart from the shallow homojunction. Some alternative device structures, they have been described here. Heterojunction between two different bandgap semiconductors have no intrinsic efficiency advantage over the homojunction. So the metal semiconductor heterojunction can be fabricated very easily. However, they intrinsically less efficient than the homojunction. The concentration of sunlight displaces the cost of photovoltaic system from the cell to the cost of the concentrating and the tracking element. Upper limit of cell efficiency at a fixed temperature increases with increasing concentrating ratio. Thank you.